Okay, today's video, last time we talked a little bit about probability distributions. And so today we're going to continue that topic. We're going to talk about continuous ones today a little bit. And we're also going to go back and kind of review a little bit here real quick. So this is section 3.3. And we'll do 3.4 at the same time, I think. Okay, so remember, discrete distribution can only come, there are only certain things that can happen. So for instance, you can order 0, 1, 2, 3, 4, 5 Big Macs, something like that. Okay. Number of phone calls you could receive in a day's time, number of texts, number of pieces of chicken, whatever it happens to be, they only come in whole number of values. Okay. So I can give you a probability distribution. This one right here is a probability distribution. Now, the things that can happen to you on this one is a 2, 3, 4, and a 5. What does that mean? I don't really know. These are the numbers that you can get, let's say, on a 4-sided dice. Cool. A 4-sided dice that is weighted weirdly. Notice that adds up to 100%, yes? Okay. And so this, because it adds up to 100%, the sum of the probabilities is 1. That's a big deal. Each of the probabilities is obviously less than 1 and bigger than 0. If it was equal to 0, like for instance 7, I didn't put there because you can't get it. If it was equal to 1, if any one of them was equal to 1, it'd be the only possible outcome. Okay? And so this is probability distribution. If I said to you, hey, what's the probability that x is less than or equal to 3, you would say it's 90%. How do I know that? Because I can get this one or this one, 90%. This is what we could refer to as this is a probability density function, or a PDF. And there's also what we're going to see as a CDF, which is what's referred to as a cumulative density function. And what that is, it's the idea that how much probability have we built up. So the probability that x is less than 2 and the one above is 0. There is none less than 0. Probability that x is less than or equal to 2, of course, 30%. Probability that x is less than or equal to 3, 90%. Probability that x is less than or equal to 4, 98%. And the probability that x is less than or equal to 5, of course, is 100%. Okay? That's what we refer to as a CDF. Now, that's a discrete CDF. Here is you. We're going to have kids, honey. Okay, great. Blah, blah. We're going to have 5 kids. Cool. So I guess we could have 0 girls, 1 girl, 2 girl, 3 girl, 4 girl, or 5 girls. There's 1 out of 32 ways for that to happen. Ditto here. Okay? There are 5 out of 32 ways to pull this off. 5 out of 32 ways to pull this off. Let's see, 5 choose 2 is 10, right? 5 choose 2. That'd be 5 factorial over 3 factorial times 2 factorial. So that'd be 5 over 3. I know I could put in a calculator. It's too hard. It's too easy. I don't care. Cancel, cancel, cancel. 2, 10. I was right. Yay! 10 out of 32, 10 out of 32. If you're playing along at home, that is 16 out of 32 plus 16 out of 32, which is 32 out of 32. Not sure why I was stressing about that. This is a PDF for the number of girls you'll have in a 5-kid family. The CDF for this, probability that x is less than or equal to x, the way the big kids write it, would be 1 out of 32. The probability that x is less than or equal to 1, that is to the left of it, you see, is 6 out of 32. And then it's going to be 16 out of 32, and then 26 out of 32, and then 31 out of 32, and then, of course, 100%, 32 out of 32. That is how a CDF works for a discrete distribution. Now, oops, almost forgot to mention something. If someone said to you, hey, what's the probability that x is bigger than 3 in this one case above up here? Well, bigger than 3 means I'm going to add these guys here. But if you think about it, that's equal to, probably x is less than or equal to, I'm sorry, let me back that up. If I add probably x is less than or equal to 3 of that, I will get 100%, yes? Well, this right here is the CDF. So if I subtract that to the other side, we will get this thing right here. We will use this trick a ton later throughout the whole rest of this book, and the rest of every time you deal with any kind of statistics, we use this trick a ton. The CDF is a built-in function, whether it's in my calculator, whether it's in Excel, what have you. The CDF is always less than or equal to. Cool, great. This is a built-in function. So then all a guy has to do then is go, oh, well, if I want this, I just find the CDF that goes with it to add up to 1. In other words, this is the complementary event to what I actually want. We know that complementary events have to add up to 100%. Boom, Bob's your uncle. Piece of cake. Okay? If you said, listen, I want x is greater than or equal to 3. Ooh. What's the opposite of that? Well, it's less than 3. Now this is not a CDF because it's not equal to. But when you're less than 3, that is equivalent to saying that you are less than or equal to 2, because you cannot get 2.5 girls. That's not possible. Because remember, this is a discrete distribution. If you're less than 3, in a discrete distribution, less than 3 is equivalent to saying less than or equal to 2. Okay, if that's in a discrete distribution only. Well, this is a CDF. And again, this is a built-in function on my calculator for many functions. The binomial, the Poisson, the not hypergeometric, come on, Jay. Geometric, negative binomial, normal, of course, and so on and so on and so forth, okay? And so, again, a CDF is a built-in function. So if you can rephrase what you're looking for, which is this, as that plus its complement in the form of a CDF, then boom, this is how you will find what you're actually looking for. Okay? In the case of this one, there's only just these 3 things to add up, and that's fabulous. But what if I wanted to have at least 3 girls out of 20 kids? Well, I could get 3 girls, or 4 girls, or 5 girls, or 6 girls, or 7 girls, or 8 girls. That's a lot of work, dude. The complement of that is less than or equal to 2. Okay? And that would, even if I do it by hand, there's only 3 things I'd have to find. So a CDF also works with continuous distributions. So we talked about this a little bit last time. So a continuous distribution, the function, of course, will be bigger than 0 for all x. That's an element of the reals that we're going to have in here, okay? So, and honestly, I don't really like that terminology. It's okay, don't get me wrong. But what it's annoying is a little bit is that people assume that it can never go negative. No. Really, I just mean on the interval from A to B. It cannot be dip negative, okay? And so, in my mind, that's all I'm asking about. For instance, let's do this guy here. So if we're going to go from, here's y equals 2x, okay? And let's do him from 0 to 1. Okay, boom. That's the height of 2. This is 1. 2 times 1 is 2. Divided by 2 because it's a triangle. This has an area of 1. In other words, if you integrated this guy over the interval from 0 to 1, you will get 1. By definition, that is a PDF. Also notice that they are never negative here. What a person would normally say is this. They would actually tell you, hey, f of x is equal to 2x when 0 is less than x, less than or equal to 1, 0 elsewhere. So in other words, it was 0 out to here. It was a piecewise function. And it was 0 from here out, but from here to here, it was 2x. That's how they get away with saying this thing right here. They define everything else to be 0. That makes sense? And so, in reality, we're only interested in over this portion here. That should be equals to. Okay. So, we will look at a bunch of them in this class in terms of integrals. But some, like just, I can make one up. Like, Jay, make one up for me. Okay, cool. So, mine is going to be f of x equals e to the negative x from 0 to infinity. Cool. 0 elsewhere. Or I could say 0 when it's less than 0. That's cool too. So in other words, my function looks like this. It's 0. And then at 0, it jumps up here to 1 and then drops off. Okay. Now, a person could prove that that is a true PDF by integrating. So what one will get is they'll get negative e to the negative x from 0 to infinity. Okay. Obviously, at the bottom end, you get minus a minus 1. Now, what is the limit as e to the negative x goes to infinity? Well, it goes to 0. So the answer is, yeah, it's 1. That's cool. Remember, that's a little bit of L'Hopital's rule, yes? And so we take that idea of this, the limit as x goes to infinity of that function. Okay? And so that's cool. And then if someone asks you, hey, listen, what's the probability that x is greater than 1? Well, you could say something like, oh, okay, well, this is equal to 1 minus the probability that x is less than or equal to 1. And you can do it a couple of different ways. It makes no difference to me. You could, on this side, simply go, let's integrate from 1 to infinity. Or you could do 1 minus, what am I doing? 1 minus the integral from 0 to 1 of e to the negative x dx. Makes no difference in either way you go it. So if you did this, it's going to be 0 minus a minus e to the negative 1. On this side over here, you're going to end up with, when you integrate this guy, you're going to end up with 1 minus parentheses. And then inside, you're going to have negative e to the negative x from 0 to 1. So you get 1 minus. And then on the top end, you're going to get e to the negative 1 minus 1. And minus a minus 1. Minus a minus 1. So if you do that, you will get, check it out, so 1 plus e to the negative 1 minus 1, which is the same thing. Meaning that it doesn't matter how you go about this. Now, had I known that this function was called the exponential function, it is, that actually is a built-in function in Excel. We'll look at that later on. And so the easy way to do that would just be to do 1 minus this CDF function. Okay, it's pretty straightforward though, pretty easy to do. Here's another one. I'm going to make one up here. Actually, I'm going to go to desmos.com. And I'm just going to make one up because I can. X squared plus 2x, you're like, but Jay, it goes negative. Hold your horses, pal. I'm going to go from 0 to 2. X squared plus 2x on the interval from 0 to 2. Now here's my question. Is this a PDF on this interval? Let's find out. Let's find out. If it is, it should integrate to 1. If it isn't, well, it won't. So it's going to be x cubed over 3 plus x squared, 0 to 2. It's going to be 8 thirds plus 4, which is clearly not 0, minus 0, which is 20 thirds or something. Okay, 20 thirds. Hey, that's not a PDF, Jay. Oh, okay, cool. Jay, could you multiply it by some constant? Would you ask me to do this on the test? Probably. And what constant would you put there for A to make this come out right? 3/20. If I put 3/20 there, what would I end up with? Well, I'd end up with 3/20 times this whole shebang. Now, is it a PDF? Yes, it is, because it sums up to 1. Okay. And again, that's just something I will probably do to make you practice. Not very hard. Pretty easy. If you have trouble integrating, or it's been a while and you're like, can you help me out with that? Yeah, this is not This is not a calculus class. I'm not going to be overly impressed if you can or cannot, or I won't be sad if you can't integrate, I guess. That's what I'm trying to say. So here's how you do it in Excel or in the computer here. Times x or comma x comma 0 comma 2. Let's see if I was right. Cool, I was right. So if I put 20/3 out front, or 3/20ths rather out front. Yay, it's 1. Cool. So if I asked you, hey, what's the probability that x is less than a half? Well, you would take 3/20ths, 0 to a half, x squared plus 2x dx. And then, of course, the guy can just come in here and go, oh, 0 to a half, done. And that's true. Yeah, and that's it. So the answer was, I didn't write down, 7/160th. Okay. Now, sometimes a person would want to know, hey, listen, Jay, can you give me what the CDF for this function is? Yeah, I certainly can, because it is a function. So in other words, I would go in from 0 up to some value x, which means I need to do this. I have to do that. People get very angry if I don't do that. Okay, they go, Jay, it's tacky to have x's in the integrand and inside on the limits of integration, which is true. It is tacky, so I won't do it. Okay, so if you were to integrate this thing, you'd end up with t cubed over 3, of course, plus t squared from 0 to x. Now, if you think about this, this is pretty cool because when you plug that in, you're going to get 3/20ths. You're going to get x cubed over 3 plus x squared minus 0. So this right here is this equals your CDF. So if you ever wanted to know, hey, what's the probability that x is less than or equal to 1/2, you simply plug it in. There's your answer, and the answer will come out the same. So I just got on a calculator here. Now, that little trick is something, again, that for ones that we use all the time, they have built-in functions for those in Excel because of that very reason. And you get that number right there, which is 7 divided by 160, if I am not mistaken. Oh, what happened? What happened? What just happened? Oh, I see what happened. See what I did? I didn't divide by 3. What a loser. What a friggin' loser. There it is. Yay! I did it right this time. Yay for me. Now, they should come out the same. Okay. Now, the cool thing about this is that in 3.4, we can... Oh, I'm sorry. One more thing I want to mention about that. So, what would that function look like? So that, remember this, when x is such that, here we do this, let's do squiggly brackets, x, no wait, back up just a minute, 0 less than equal to x, less than equal to 3, no, 2, boom. And then I'm going to say 0 when x is less than 0. And I'm going to say x is equal to 1, or yeah, y equals 1 when x is greater than 2. That's fine, yeah. Now, you're like, Jay, what's going on here? Because I feel like, what does this red line represent? Remember, the red line represents our PDF. What we need to look at is our CDF. We never graphed that yet. Oh, you hippie. Nice. Oh, that's hot. Now, when x is 0 to x to 2. What happened to my 0? Well, that's hot. So what you'll see is this. It's 0 until we get to 0. Then we start building up probability according to this red line. And we're building and building and building. And when we get there, oops, well, not quite according to the red line. Let me back up. The red line isn't quite right, remember. We need to figure out our 3/20ths in there. Oop. So we're building up probability according to this red line, but we're stacking it. As that probability builds up, the area under that red line becomes this purple line right here. In other words, this purple line is the integral of that red line right there that we're seeing. Okay? And so when we do that, we end up with this function. Then from here on out, it'll always be at 100% because we're never going to pick up more than 100%. It just doesn't work that way. Okay? And so, yeah, that's how it works. It's pretty good, I think, ish. Something just looks a little weird about that, but no, I don't think it is. Anyway, there it is. That's it. That's all. Now, yeah, that's it. So again, our red line, so it was blue to hit the red, then it went up to red, and then it would have been 0 after the red line, okay? Because that's how our probability was. That's where the probability is. Now, the cumulative distribution, we didn't have any until we got to 0. Then we started adding it according to the purple line. And we get up here to 1, we are staying at 1 forever after that. It's never going to get any lower than that. Okay? It's not going to get higher either. Cool. Now, that's all a CDF is the antiderivative of, it's the antiderivative of the PDF. Now, here we go. Let's do this. So, suppose you had a PDF that was equal to 5e to the minus 5x. No, 1/5. There we go, I think. From x goes from 0 to infinity. Remember, you can't equal infinity. That's just weird. So if I tried this is my PDF. If I tried this to see what happens, let's see if, in fact, it is a PDF or not. Remember, if it is a PDF, what should happen? It should integrate to 1 over the whole thing. Now, it's been a while. You can't remember how to integrate this. A little substitution, you know. If you're trying to impress the ladies, it would be substitutions, how you do it. But I don't need to impress anybody here. So I'm just going to go like that. And I'm just going to do like this to get the antiderivative. So, oops. I wanted that to be a 1/5, I guess. Sometimes a Mr. Groom forgets things. That's what I wanted. Thank you. There you go. So the question is this a PDF? And the answer is, I think so. So this becomes e to the negative x over 5 from 0 to infinity. Take the limit as x approaches infinity, and you will get 0. Minus a minus, and then if you put in a 0, you get minus a minus 1. So the answer is 1. That's great. What would happen if I wanted my CDF? Well, then I would integrate from here. And I would end up with this and this. And I would end up with negative e to the negative x over 5 minus a minus 1, or 1 minus e to the negative x over 5. This is the CDF for this guy. Well, that part right there, that guy right there. Okay, so this would be the PDF, probability density function. This down here would be my CDF for this guy. Remember, this guy always tells me the probability that x is less than or equal to some value of x. For instance, x less than 2 or what have you. Okay? Now, that's all fine and good. What if I had a joint PDF? What if I had a joint PDF? That is, it's a function of 2 variables. The probability, in other words, it could be written as, typically it would be written as f of x and y. Now, because I feel like it, I'm going to start off with a continuous distribution. And so when I do a continuous distribution, some function of x and y, and I'm trying to think of a nice easy one here, x, y, dx, dy, from 0 less than x less than 1. Is that what I want? I think. No. Yeah, I think so. 0 less than y less than 1. Let's see if this is true. In other words, this thing here had better integrate over, well, technically from everywhere across the board, better integrate to 100%. First of all, that's a true statement, just like before, okay? And all of the probabilities better be positive, of course, on the region that we're talking about, okay? And that's all fine and good. Now remember, we just define it to be 0 everywhere that's not on this interval. We just define it to be 0 there. And so functionally speaking, what we have is 4xy dx dy 0, 1, 0, 1. And if it's been a while for you, please by all means use the calculator. So 4x, don't forget to times y like that, comma x, comma 0, comma 1, comma y, comma 0, comma 1. Uh-oh, I biffed that one, didn't I? Oh, I know why. Hey, maybe if you're going to do a double integral, you got to put 2 integral signs on there, you goober. Duh. Yay, it's 100%. Woohoo! And so, because it equals 1, check, it is a PDF. That's nice. Could you find the probability that x is less than 0.7 and y is less than or equal to 0.2? Yeah, probably. How would I do that? Well, I'd integrate 4xy dx dy 0.7, 0.2. Now, I harped last week or some time ago on 0.0196. Independent functions, right? Or independent variables. If you look at this function, you're like, it doesn't look like x and y have anything to do with each other. In fact, if you had me for Calc 4, I kind of preach this. If you're integrating over the x and y over a rectangle down here, they don't really seem to have much to do with one another at all. That's part of it. That's not all of it. That's part of it for sure, though. And so, in fact, these guys are actually independent functions. And we're going to show you a couple of them that are like this. Here's an example of one that is also independent. Suppose I said, hey, look, f of x is distributed like this. 0.2 x. Well, I'm going to pause for a second, make sure I get a nice good one for you. I don't want to have to fiddle. Okay, so here's a couple of functions. So I have that x is 0.01x from 5 to 15. And I have g of y is 2y times this. Remember when I asked you what's the probability of x and y happening, and I said, hey, listen, they're independent events. Wasn't it true that you took the probability of x times the probability of y? Right? That's exactly what we're going to do here. We're going to take 0.01x times 2y. That's because these guys are truly independent. And it turns out that when I do this, I will end up with now a function of x and y, which is 0.02xy, 0 less than y less than 1, and of course 5 less than x less than 15. Okay, this is a PDF, and it's a independent PDF. Okay, that is x and y are independent of one another. It turns out that there's a rule here, and it says this. These original guys right here are actually referred to as what are called marginal distributions. They are the marginal distributions of x and y. And if the joint distribution PDF we'll call it, is equal to the product of the marginals, x and y are independent. Okay. Now we're going to look at this in a little bit, and we're going to see if we find some other ones that are independent, starting from here. In other words, we're not going to start with the marginals and build up to this. In fact, we might start with a joint distribution, and what may not really look like it's independent, but it may in fact very well be independent. We'll talk about how we're going to get to there. Okay. Again, how do I check if this is independent or not? Well, how do I check to see if this is a true PDF or not, rather? Well, I go ahead and integrate it. Take the double integral. And it works. Yes, that's awesome. Okay. But it gets better, friends, because what if one were to do this? In other words, let's integrate the y's out of this thing. Well, what you're going to be left with is some function of x. And we call this the marginal of x. And if you were to integrate with respect to x across him, what you'd end up with is the marginal of the y's. Because all you have left is y values. Let's see if this is true. Again, what you're doing is you're getting rid of the variable that you don't want anymore. .01x. I feel like I've seen that before somewhere. And y. Again, I feel like I've seen those guys before. So the question is, will always be, does this times this equal this? If it does, then you have independent events. Now, again, we won't do it that way. Okay, we'll either tell you that they're independent, in which case just multiply them to get the joint, or we'll say here's some random joint function. Are the x and y independent? How will I do that? Well, I'll integrate the y's out. I'll integrate the x's out. I'll get the two marginals. And I'll see if the product of the marginals is the joint. And if it is, then yay, they were independent all along. Now, these marginal distributions are good for a lot of things, and we're going to talk more about them in a little bit. Especially they're good for conditional probability, obviously. So the reason, we're going to talk about the reason that they... we're going to talk a little bit more about the reason that... they're called marginals in a little bit. It has nothing to do. It really has nothing to do with the anything other than you'll see it once I show it to you in the discrete format. In the discrete format, like that makes sense. In a continuous distribution, it doesn't really make that much sense. Here we go. So each rear tire on an airplane, this is number 44 in your book there, is supposed to be filled with pressure of 40 pounds per square inch. Cool. And the x is the actual pressure in the right tire, y is the actual pressure. There they are. Suppose x and y are random variables with a joint distribution. And here it is. They haven't asked us any questions yet. They want us to find k that makes this work. And 30. Notice that they did not put an equal sign on the 50. Here's a question. Does it matter? And the answer is no. We all know that when we are integrating, whether it equals that value or not is not important, because the integral actually happens at the limit as you approach that value. Okay? So here it is. That's cool. How would I find k? Well, to find k, I would simply integrate this. And whatever I have left over, you know, if it equals 5, then my k is 1/5. It's whatever I need to multiply to make the whole shebang come out to be 1, like it's supposed to. So I got that god-awful number, which is just disturbing, which means that k is equal to 3 over 3.9. Four zeros. Nice, that's my k value. You with me? So that's that. That's nice. So then it wants, so what is k? Well, I just told you what k is. Find the probability that x is between 30 and 40. This is another part of the problem. And 40 is less than y is less than 50. Okay? So all I have to do is come in here and change. Well, I have to do a few things. Change my limits of integration from 30 to 40 and from 40 to 50 and hit enter. That's 1/4. Okay? And then find the probability that both tires are underfilled. So they're supposed to have a pressure of 40 pounds in them. Okay? So what we want to know is what's the probability that x is less than 40? Less than 40. Remember, less than or equal to less than potato, vodka. Because what is the probability that you land on exactly 40? Well, remember, with a discrete, I think I mentioned this the other day, with a discrete distribution, you can land on 40. But with a continuous distribution, there's an infinite number of numbers across there. So it'd be equivalent to saying this. Hey, what's the probability that at x equals 40 would be equivalent to the integral from 40 to 40 of any function, which we all know is what? 0. That's the way I like to do it calculus-wise, but from just a regular person's standpoint, there's an infinite number of numbers from here to here, yes? What's the probability you end up on that one exactly? 0, because it's 1 out of an infinite number of them. So I don't care how you think about it, that's fine. Now, look, I can put in negative infinity to 40. That's true, but I wouldn't do that because the tire can only be from 30 to 40, okay? So anything less than 30 is just going to be a 0. Are you with me? So that's all we would put in. Oops, what happened? We just go from 30 to 40. So 37 out of 196, or if you prefer, 0.1, about 18, about 18, 19. What are you doing, jackass? About 18.8%. Okay, cool, great. Now, could I find the marginal of x on this guy? Probably. Let's do it. If I want the marginal of x, I would simply get rid of, oh shoot. Let's integrate the y's out. So the y's go from 30 to 50. You gotta get rid of one of the integral signs too. And you get that mess. Okay? And while we're here, I'm just going to find the marginal with respect to y. Oh, it's that thing. Now, here's my question. Times, parentheses, this thing, parentheses. Yeah, that thing right there does not equal 3 over 3,920,000 times x squared plus y squared. So what does that mean? On this problem, x and y are dependent. They're dependent because the marginal, the product of their marginals, is not equal to the joint. Why would their tires be independent or dependent, Jay? I don't know. I just know that's the answer to the question, sir. I can't tell you. I haven't been involved in this particular scenario. In real life, there will be reasons why it's this or it's that or the other thing. Okay. Here we go. So x and y denote the length of life in years of two components in an electronic system. If the joint density function is e to the negative x plus y, 0 elsewhere, x bigger than 0, y bigger than 0. In other words, 0 to infinity, 0 to infinity. Okay? That's cool. So if that's the PDF, then the question then is they're going to ask you is this question here. What's the probability that x is 0 is less than x is less than 1? And let's do this one here. Y is less than 3. Okay, let's do this one here for fun first. Okay, so if I do this one first, then we'll go take a look at what else we can do with this guy. So first and foremost of all, here we go. So e to the negative parentheses x plus y parentheses comma x. Oh wait. Comma x comma 0 comma 1 comma y comma 0 comma 3. About a 60% chance of that happening. You with me? Cool. Nice. Now here's a question. Can you find the marginal distribution of x? Well, here it is. Oops, it's the integral negative x plus y dy 0 to infinity. And let's see what that comes out to be here. E to the negative x. Well, I wonder what the marginal with respect to y would be. Well, it doesn't take a rocket surgeon to see it's going to be exactly the same, right? Oh, you idiot. It's up to you to change that to an x. I want to try it with an x. There we go. Nice. Hey, what is e to the negative x times? Oh, you get that. Hey, what is that? That is a fancy way of saying this. Am I right? So what does that say about on this problem? It says on this problem, x and y are independent. Nice. Again, because the probability, the joint distribution is equal to the product of their marginals. Because that's true, they are independent events. Okay? Now, here's a fun noise. Remember back in the day we talked about this. Hey, what is the probability, or what is the probability, probability that x is something, that this happens given that y happens. How would you do that? Okay, remember, that was the probability of x and y on top over the probability of y alone, right? Because y is the one that happened first, correct? So then you're going to say, well, that's weird. How's that going to work? Well, if you look back on page 99 is where it shows this. This right here, this guy is equal to f of x and y, because that's the probability of x and y happening, yes? All right, over, they write h of y, but this is the marginal of y, marginal of y. Okay? And of course, if you're doing it the other way around, if you're going to condition y, condition it on x happening, then of course it's the joint over the marginal. And they always use g of x in this book for the marginal of x. Now you're like, this is now if you sit in your seats now, you get a grip on your seat because this is going to be mind blowing. Okay, let's do this one here for the previous problem. Check it out, friends. For the previous problem, okay, we know that our joint was this guy here, right? Or if you prefer, maybe you do. I don't, but maybe you do. This guy, right? Now, if I divide by the marginal of y, I get this. And what are you left with, friends? You're left with e to the negative x. Are you with me? Isn't that pretty cool? So then if you want to solve it, just solve it. So check this problem out. So the problem for the one that we just did asks this question. It asks the question, what's the probability that x is between 0 and 1 given that y equals 2. They are independent. They are independent. I don't care what y is. So the answer to this question is simply this. You could obviously set it up like this and go e to the negative x minus y, or this way, whatever makes you happy, over e to the minus y dx well, I can do it either way, I guess, but I wouldn't set it. I would set up like this first, and then I'd be like, oh, wait a minute, here, check it out, these guys cancel off, so what I really left with is I just have one integral now. I'm going to integrate it from 0 to 1, and so the answer is going to become 1 minus e to the minus 1, whatever that is. %, or thereabouts. Okay? Pretty sweet, pretty easy to do. Remember, when I condition if I condition one independent event on a different independent event, it doesn't make any difference because, well, they're independent. What part of independent do you not understand, sir, ma'am? Okay? They don't have anything to do with one another. Okay? Ooh, now, here's a little fun one. Very nice, very cool. Right off the bat, you see this guy here, f of x and y, is equal to 6x. Careful now. So when you look at this, you're like, oh, wait, 6x, that's right. So 6x, we're going to integrate the underneath that curve, but x goes from 0 to 1. And y goes from 0, that's right here, up to 1 minus x. So this guy. So because the boundaries of y depend on x, what does that sound like? It sounds like it's a dependent problem right off the bat. Okay. So if someone asked you in this problem, hey, are they independent or dependent? They're dependent. There you go. So first of all, let's double check that this is in fact a PDF. Oops. Yay, it worked. All right. Now, what do they want us to do on this problem? Well, they would like us to find, so that x and y are not independent. Okay, well, I pretty much already did because y depends on, the boundaries there depend on one another. But I can do it. I can make this happen, friend. Okay, so if I integrate with respect to y, and just integrate the y's out of this thing, I get that thing. And if I integrate with respect to x, hippie, I get that thing. And when you multiply those together, you also do not get that. Okay? But more importantly, they're not because they depend on one another that way. Okay? And then it wants me to find probably that x is greater than 0.3 given that y equals 0.5. Okay? So let's back this up a little bit now. So in this problem, we had 6x. That is our joint. our marginal of x was equal to 3. No, I'm sorry, our marginal of y was equal to 3, sorry. Marginal of y was equal to 3, because that's the one I integrated with respect to x. And our marginal of x is negative 6x x minus 1. Okay, so when I'm looking for the probability that x is greater than 0.3, given that y equals 0.5. Cool. So when I set this problem up, it's going to look something along these lines. You're going to say, all right, well, it's 6x over 3, which is just 2x. So I'm going to integrate 2x from 0.3 to, where are we going on this one? Up to 1, because that's the biggest that x can ever be. Let's see what happens. .91. You're like, what did I do with this y equals 0.5, Jay? Exactly, you don't in this case, because there's no y in the problem. Okay, if the y had been in the problem, I would shove that in the place of y in that case, and be good to go. Okay. Let's see if we can find one that's similar to that, and I can actually do one that is perfect. Yeah, I'll do that one there just for fun, I guess. Yeah, let's do him. So the joint is equal to 6 minus x minus y over 8. 0 less than x less than 2. 2 less than y less than 4. 0 elsewhere. Okay. So first of all, it wants the probability that 1 is less than y is less than 3, given that x is equal to 1. Cool. Well, let's see what happens here. Well, first, I need a marginal of x. So we know that's the integral of 6 minus x minus y over 8 dy from 2 to 4. What? Oop, that's disturbing. Sorry. So negative x minus 3 over 8 over 4. So this is the marginal of x. Awesome. So what I want then is 6 minus x minus y over 8 over negative x minus 3 over 4. And if I clean that up a little bit, I'll get this minus this over this times this over this. And so I'll end up with 6 minus x minus y over negative x minus 3. Okay, so I'm going to integrate this sucker here. Are you with me? I'm going to integrate it with respect to who this time? Okay, well, I want to respect to y. I'm going to integrate it from 1 to 3. But what about my x's? Well, we just were told that x equals 1. So this is going to become 5 minus y on top over 1 minus 3 is negative 2, so positive 2. Let's see if it works. I'm dying to know. Okay, somewhere I dropped something. Something went boop bye-bye. Oh, that's what went bye-bye. My 2 right there, you with me? My 2 went bye-bye. So that makes that actually a 4 down here, which makes me a little happier. Still something a little screwy. Oops. Yeah, still a little screwy there. Let's see what I did wrong. Let me pause you for a second while because I'm an idiot. Okay, I'm an idiot. Come back up here and look where y goes, friends. Look where y goes. Y only goes from 2 to friggin' 4. They want me to go less than 2. I ain't doing it, bruh. Let me back this up a little bit. So I'm going to say it's 0 plus this is equal to what I'm looking for. Are you with me? That is where I went boo-boo. So let's try this again. So I'm going to integrate this baby with respect to y from 2 to 3. Ugh. Boy, that's embarrassing. I don't know why I didn't catch that. Anyway, remember, that is, yes, 5/8. Yes, that makes me happier. Better be less than 1, friends. But that's a huge deal. It's 0 elsewhere. Are you with me? So the probability that y is between 1 and 3 is equal to the probability that y is between 1 and 2 plus the probability that y is between 2 and 3. We know that this piece here is 0. We know that then this is an integral from 2 to 3. Okay, don't mess that up. Okay, be careful. Now, that's discrete. I mean, continuous. I think they're the easiest to do, to be quite honest with you. I think they're the easiest to do. I think the other ones aren't hard, but I think people always mess them up. What I'm going to do is I'm going to list out 2 dice. What I'm going to do is I'm going to roll 2 dice, just like in Yahtzee or in Monopoly or something. And what I'm going to say is that each dice we know is independent of one another. Well, duh. And so, of course, you could get a 1 and a 1, obviously, right? So there's 36 outcomes. So you can get a 2, you can get a 3, 4, 5, 5, 5, 5, 6, 6, 6, 6, 6, 7, 7, 7, 7, 7, 8. Right? There's 36 outcomes in there. Is that true? So probably each one of these guys is 1/6. That makes sense? So if someone asks you, what's the probability you could roll a 6 on 2 dice? Roll 6 on 2 dice. And it's clearly there's 1, 2, 3, 4, 5. Wait. Yes, 5 ways to do that. 5 out of 36. Done. Piece of cake, right? Now, what would the marginal distribution be? Jay, what do you mean for the first dice? I don't know what you mean, Jay. Well, here's the deal. We're going to sum across the rows. So look, there's 1/6 here, or I'm sorry, 1/36 here. Oh, I'm sorry, each one of those should have been 1/36. There's 1/36 chance of this happening, 1/36, 1/36, 1/36, 1/36. There's a 1 in 6 chance that I get a 1 on the first dice. Hey, that's also true for here, 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 and here. Notice that those are in the margins. Do you get it? That's why they're called marginals. Same thing is true here. The marginal for the second dice, we're going to then add down the columns, and you will also get 1 out of 6 down here. And because the distributions here, if I take 1/6 times 1/6, I get 1/36, because the product of the marginals is the condition. I'm sorry, the product of the marginals is the joint. Then we say these guys are independent of one another. Okay? It's pretty straightforward kind of a deal. It's almost fun, actually, when you think about it. Okay? Not a very hard concept to mess with here at all. Here's one that's the book gives here. I'll just do this one and we'll call it a day. So X and Y are the following joint PDF. So you can get a 2 or you can get a 4. That's it on X. And on Y, you can get a 1, 3, and a 5. And then here are the probabilities. And of course, when you sum them up, 0.1, 0.2, 0.1, 0.15, 0.3, 0.15. when you sum them up, you will see that you get 25%, you get 50%, and you get 25%. These are the marginals for y. And for x, they are 40% and 60%, right? Nice. So then the question might be, are these independent of one another? I don't know. Let's find out. How did you get 0.1? Do you take 0.4 times 0.25? Well, actually, yeah, that's right, Jay. And is 0.2 equal to 0.4 times 0.5? By God, it is. And is 0.4 times 0.25 equal to that? Yeah, it is. What is 60% of 25%? Well, if I was a betting man. Nuh-uh. Now, no way. How about that? And then 60% of 50% is 30%. What? Look, x and y are independent. I always find that just because I felt like it. You with me? So here's the problem. Find the marginal of x and find the marginal of y. Oh, geez, I already did that. Okay, cool. There they are. This is the marginal of y. This is the marginal of x. What about this? What's the probability that x is less than or equal to 3 and y is bigger than 1? Well, I don't know. Let's find out. So, y bigger than 1. So that would be these 4 boxes down here, yes? Oh, I meant x is less than, or let's do x less than 4. I was looking at the y. I'm sorry, I wrote that. Sorry about that. So let's do x less than 4. Now, of course, you're like, well, wait, isn't that just x equals 2, Jay? It is, in this case, sure. Greater than 1. That's great. So you could also say greater than or equal to 2 if that makes you happier. So wait, so we're saying, basically we're saying these 2 rows, or those 2 boxes added together. That's right. That's it. There's nothing to those guys. What's the probability that y is greater than or equal to 3 given that x equals 4? Well, first off, they're independent, so I'm not going to fool with it. I'm just going to go with it. Probability that y is bigger than 3, bigger than or equal to 3 is 75%. You with me? Boom, done. It's pretty straightforward. Because why is that? Because they are independent. I don't care what x is doing. Okay, x can be whatever x wants to be. Don't care. I couldn't care less. Because they are still going to be the same problem. Okay. Wait, hold up a little bit there. Right, but here's the thing. Given that x equals 4, in other words, so if you look at this, all I'm interested in is in this column right here. Are you with me? That's all I'm really interested in. Now you're like, well, how'd you get 75%, Jay? Isn't it true that it's 0.45? Kind of. You're right. It's those 2 boxes right there. It's the only thing I'm really interested in, right? However, it's those 2 boxes out of this whole column. So out of 60%. And what is 45% out of 60%? 75%. What? So here's the deal. Because I know they're independent, I just come right over to here and I go with 75%. That makes sense? If I did know they were 75%, then I would go ahead and add them up like that. Okay? That should take care of section 3.3 and 3.4 for you. Let me know if you have any questions.